Good. Hi. Okay, good morning, everyone. Thank you very much. It's always a great pleasure to be back in Santa Cruz. Thank you to the organizers for, again, giving me the opportunity to come and give you some recent updates about our study of the evolution of cold streams in very massive galaxies. I think this is the perfect time for an update because just this year alone, we had 3 papers out on the topic. So I think it's a good time to tell you all about it. Okay, jumping right in. We know that galaxies form in the cosmic web. Now, very, very broadly speaking, there are 2 main types of galaxies that you can find, or 2 types of halos that you can find in this image. Your typical halos, which are of order the Preshechter mass or slightly lower, reside in single, very large filaments compared to their size, and they're fed in a pretty spherical isotropic fashion. But if you go to your very massive halos, your high sigma peaks, they lie at the nodes of the cosmic web, and they're fed by a few very thin, very dense filaments which come from a few random directions. Now, this filamentary structure is not just observed in the dark matter, it also exists in the gas, and it's very important for the growth and the evolution of galactic disks. So I'm going to show you a movie here from the Vela simulations, which we've heard about already this week. This is from redshift 6 to redshift 4 of a galaxy that has a virial mass of 2 times 10 to the 11 solar masses at redshift 6. I want you to notice 3 things as you watch the movie. Number 1, the galaxy is fed by 3 streams which seem to go almost all the way to the center of the disk. And the 3 streams seem to lie in a plane. Number 2, the streams do not directly hit the center of the disk. They're not on purely radial orbits. There's an impact parameter of about 30% of the virial radius. That number is going to come back. And it's that impact parameter which actually spins up the disk and grows the angular momentum of the disk. And the third thing is, as the streams approach this interaction region of 30% of the virial radius, a lot of messy clumpiness and instabilities happen. Okay, and that's what drives what we call violent disk instability in these galactic disks. And it also drives various instabilities in the streams themselves, which we'll talk about during the rest of the talk. So you can see here the streams really contributing coherently to the angular momentum growth of the disk as they spiral in. You can see the clumps forming where the streams begin to interact with the disk and begin to interact with each other. Now here you might say, hey, wait, where did the streams go? So okay, there are 2 things. Number 1, that 0.3 times the virial radius, which I said was the interaction region, has grown because we're at a later time, so you can't really see it. It's almost outside the size of the box. And number 2, the plane where all the streams were located has shifted. So it's no longer perfectly aligned with the plane of the disk, but we've had a shift in the angular momentum. That's also very important and interesting, but I won't talk more about that during this talk. Okay, we can skip this. The rest isn't all that interesting. Now, we think we are beginning to see these things in observations. We had a really nice talk by Chris Martin on Tuesday, and I took the slide from him, where he's seeing very massive galaxies at very high redshift, where you see on scales of 100 kiloparsec or more, the virial scale of the halo, you can see gas which he claims and he sees might be flowing in toward the disk in a spiral pattern that very much resembles the movie we just saw. So let's for the moment assume that streams are actually real and that we're actually beginning to observe them. I should note very similar observations by Muse and very similar observations seen not in emission but in absorption in the CGM of halos. So if streams are actually real, what galaxies do we expect to be stream fed? So a rule of thumb, if I want to wave my arms a bit, is that you can argue a 2 sigma peak in the cosmic density field is going to be stream fed. Now, what's a 2 sigma peak? Well, that's basically this black line here. The virial mass of the 2 sigma peak is a function of time. This is the 1 sigma peak, or the Preshechter mass. And these are various curves which show the typical average evolution of different redshift 0 halo masses. So at redshift 0, the only halos we expect to be stream fed are the most massive clusters, anything above 10 to the 14 solar masses. But if you look at the progenitor of the Milky Way, it was probably stream fed at redshift larger than 3. If you look at a typical dwarf galaxy at redshift 0, you take it all the way back to redshift 6, it might very well have been stream fed as well because it was a 2 sigma peak at redshift 6. So these streams were important in the evolution of almost every galaxy at some point during their evolution. Now, for the rest of my talk, the first part I'm going to be focusing on this regime, your halos that are of order 10 to the 12 solar masses at redshifts between 2 to 4. And then in the final few slides, I'm going to discuss what might happen here at redshift 6 in less massive halos as well. So why is this why is this scale of 10 to the 12 solar masses that I mentioned so interesting? Well, we know that at that scale and above, we expect halos to have, we expect the CGM to contain hot gas at the virial temperature. They're stable to virial shock heating. The cooling time becomes longer than the dynamical time, and therefore this gas cannot cool and it cannot fall down to the galaxy and form stars. However, it's been hypothesized that at high redshift, when these galaxies are fed by these very thin, very dense streams, since the gas in these streams is so much denser than the surrounding gas, the cooling times are so much shorter, the shock is unstable, and these things can basically plummet all the way down into the disk and can form stars. We saw some potential evidence of this in Peter Baruzzi's talk on Thursday. But the question is, do these streams actually make it all the way down to the central disk? It's not at all obvious. If you go to cosmological simulations, again using the Severino et al. Simulations, we see that at about 30% of the virial radius, as I said, there's a messy interaction region where this is clearly not a well-defined coherent stream that makes it all the way down to the center. If you go to the Arepo simulations, they would say, 30%, that's not even good enough. At 50 to 70% of the virial radius, the streams mix and they heat and they basically disappear. But you shouldn't believe them, and you shouldn't believe them, or us, because the streams in these simulations are really marginally resolved, 20, maybe 30 cells at best in these cases. And that's not enough to really resolve the detailed hydrodynamic instabilities that are going to affect these streams as they travel through the CGM. And indeed, streams may break up due to shocks, hydro instabilities, thermal instabilities, gravitational instabilities, collisions between streams, a whole mess of things. And this warrants a more detailed, idealized study of the dynamics of these things. On the observational side, this is from the Muse group, a very nice paper from 2016, where, again, they looked at 17 bright radio-quiet quasars at redshifts 3 to 4, and they found giant Lyman alpha nebula in extending up to 100 kiloparsecs from the center in all of their cases. Now, while a few of these might look like filaments, most of them don't. So what's happening to the streams? Are they somehow mixing and becoming spherical? And also they made a very interesting point that a large fraction of the gas seems to be in dense, cold, small, and metal pore clumps, which might indicate some kind of fragmentation process occurring in the streams as opposed to the coherent structures that we had in our minds 10 years ago. So as a first step to studying this in a systematic way, I'm going to show you a toy model for Kelvin-Helmholtz instability in these cold streams. You have a hot halo, a cold stream, and a galactic disk. The stream has a temperature of about 10 to the 4 Kelvin because it's very low metallicity, and that's where the cooling rate becomes quite small. The halo has a temperature of about 10 to the 6 Kelvin, because that's the virial temperature of the system. And if you assume for the toy model, the stream and the halo are in pressure equilibrium, you can get a density contrast of anywhere between 10 to 100. Now, the streams are flowing into the virial velocity, and the sound speed in the hot medium is also about the virial velocity. That's what the virial temperature means. And that means that if I define the Mach number as the ratio of the stream velocity to the sound speed in the halo, you get a Mach number of anywhere between 0.5 to 2. Note that that means the Mach number with respect to its own sound speed is very supersonic. It's larger than 10. Now, under these conditions, back in 2016, we did a linear stability analysis, and in the function of the density contrast and the Mach number and the thickness of the stream compared to the virial radius, we found that for a large range of parameters, you can get a large number of e-folding times within one virial time, up to like 100. Now, clearly, I don't mean to imply here that the perturbation has grown by a factor of e to the 100. That would be silly. What I do mean to imply is that we're deeply in the nonlinear regime, and we have to study this in a lot more detail. And a technical point which I won't go into a lot more detail of, you'll notice this kind of phase transition here in the diagram. That's because the Kelvin-Helmholtz instability itself undergoes somewhat of a phase transition from the familiar surface modes, which is what we all learn about in our undergrad classes, to slightly more complicated things known as body modes, which manifest themselves in a very different way. You can talk to me about that later if you want, but that's the reason for this sharp jump here. Okay, now, what does nonlinear stream disruption look like? So these are for the surface modes, these are for the body modes. Here you begin to form the familiar Kelvin-Helmholtz rolls, and then they merge and they grow, and they basically eat the stream out from the outside in until you're left with a very turbulent mixing zone. The body modes are a bit different. You form kind of a large-scale sinusoidal pattern at first, but then again, eventually you wind up with a very mixed, very turbulent state. And the important thing is you can derive analytically the time scales for each of these two processes. you find that they scale as the stream crossing time. In other words, they're shorter the narrower the stream is. It's kind of intuitive. And if you put all that together, you can ask, okay, what is the smallest stream that can survive the nonlinear Kelvin-Helmholtz instability for a virial crossing time? And again, it's going to depend on the density contrast and the Mach number. There's a certain dependence on the initial conditions, although it's rather weak. You can talk to me about that later. And the point is that in the range between 0.5% for very dense, very fast streams, and up to 5% for your more typical streams, they can disrupt and lessen the virial crossing time. And basically, streams that are narrower than 5% of the virial radius have the potential to completely disrupt and mix due to Kelvin-Helmholtz instability in the CGM. What is the effect of that? Well, for one thing, it can drive turbulence in the CGM. In fact, we find that for all the simulations that we ran, I don't care if they're surface modes, body modes, I don't care if the density contrast is 1 or 100, you always wind up at about the time when the stream finally disrupts with a turbulent velocity that's of order 40% of the initial velocity of the stream. Now, it's true that most of this, 0.4 times v is on large scales and is driven by shear. But once you go down to scales that are of order the size of the stream and smaller, the turbulence becomes very isotropic. The turbulent Mach number is of order unity. And the spectrum is really close to Kolmogorov, which in these units would be a flat line. So we're really driving well-mixed turbulence in the CGM, in the streams after they've disrupted. Now, this also leads to a log normal density PDF, which I'm not showing, which has overdensities of up to a factor of 2, with no cooling and with no gravity at the moment. When you put in cooling and gravity, as we'll see, this will increase quite dramatically. Now, the other very important phenomenon is Kelvin-Helmholtz instability causes streams to decelerate as they go in. And you can actually work out, again, analytically, what that deceleration time scale should be as a function of the density contrast, the Mach number, and your geometry. Are you a 3D stream or a 2D stream? And you can work out what the deceleration rate is supposed to be. And again, it's a good match to all the simulations. And when you do that, and you couple it, you model it as a friction force that acts against the halo gravity, you can compute a velocity profile for the streams in the CGM. The black line here is the free fall velocity. And the different lines here are the velocity profiles that we get for different stream thicknesses and different density contrasts. And the takeaway point is that 30 to 70% of the gravitational energy gained by falling down the potential well can be dissipated through Kelvin-Helmholtz friction. And that's more than enough needed to power the Lyman alpha blobs that we see. So this is a viable mechanism for fueling the Lyman alpha emission that we can see. Now, as I said, that so far it was without cooling, without gravity. What happens if I put in cooling? Well, it dramatically changes the disruption of the stream. The stream no longer expands and mixes into the halo. Rather, the halo condenses onto the stream and increases the density fluctuations. This is work in progress. But the important thing with regard to my final point, the deceleration rates are unaffected. So my previous point about how much energy can be dissipated as it flows in is still valid. Okay, and this is just an advertisement. We're going to hear more about this later today. This is a cosmological simulation with tailored refinement on the streams themselves, 75 parsec resolution all along the stream. And you can see here the Kelvin-Helmholtz instability beginning to develop until eventually, as you get down close to the center, the stream really does begin to fragment. So there is some merit to all of this analysis. Okay, skipping ahead in my last 2 minutes to what happens at high redshift in stream-fed galaxies. I'm showing you again the Vela 19, the same galaxy that we saw the movie of, 2 times 10 to the 11 solar masses at redshift 6, the dark matter, the gas, and stars that are younger than 100 million years. And this is the virial radius, and this is 0.3 times the virial radius. And I've highlighted here very dense gas clumps that are forming stars, but have no associated substructure in the dark matter. Now, this is not a projection effect, because if you go into the 3D distributions of gas, stars, young stars, and the dark matter, you look at the total mass and the bound mass, none of the dark matter that's there is bound. It's all part of the background. But all of the baryons, or certainly almost all the baryons, are bound. A total baryonic mass of about 5 times 10 to the 7 solar masses with no dark matter, star formation rates of order 0.2 solar masses per year, very low metallicity, consistent with metal pore globular clusters, which is the point I'm trying to get to. And this seems to be fragmentation of streams due to gravitational instabilities out in the halo. Now, the first thing my wise PhD advisor had taught me was that you should very rarely trust simulations at all, and you should never trust them blindly. So when you see something in a simulation, you have to try and understand it with a simple toy model. Thank you for that, Avishai. So that's what we did in this paper. So we tried to come up with a toy model for the properties of streams as a function of halo mass and the function of redshift, and when we might expect them to become gravitationally unstable, cool and form stars. Unfortunately, as my chair will tell me, I do not have time to go into the details of the model. I will refer you to this paper and leave you with a few key take-home points. If you go through the model, I'm sorry, at very high redshift, at redshift 6, depending on three free parameters, which are the accretion rate on the stream, the velocity of the stream, and the size of the gas stream with respect to the size of the dark matter filament, you can get central densities in these streams between 1 to 20 atoms per cc, which is pretty high, a lot higher than you expect to find in the CGM. The streams are very turbulent due to accretion onto the streams, Kelvin-Helmholtz instabilities, which we just saw, and also due to galactic winds. And when you put everything together, you get, as I mentioned, you can get turbulent Mach numbers of order unity, but that scales with the halo mass and with the redshift. Now, gravitational in isothermal cylinder is unstable to collapse if its mass per unit length is larger than a critical value. And indeed, in the model, the streams exceed that critical value at high redshift for very massive halos. We expect them to be gravitationally unstable. Stay tuned for the next talk by my student Han Ong, which is going to complicate this picture a little bit. This is going to lead to a sausage instability followed by local collapse on the gene scale. The gene's mass in this case is 10 to the 7 to 10 to the 8 solar masses, consistent with what the simulations are showing us. The free fall time is about half the virial crossing time, so there's more than enough time for these things to actually collapse. And can they cool below 10 to the 4? Well, in this model, for about 1 or 2% solar metallicity, considering C2 emission, which was motivated by these studies, at redshift above 5, the streams are dense enough to allow cooling down to 100 Kelvin in less than the virial crossing time. So this is consistent with what we see. I will just say this can be relevant for globular cluster formation. The pressure in the center of these streams above redshift 6 can exceed 10 to the 6 Kelvin per centimeter cubed, which is what you need for globular cluster formation. And this gives you a lot of really good properties for globular clusters. I won't really go into the details. A second implication, do we believe that there are galaxies without dark matter? I don't know. But if there are, maybe that's where they came from. Just saying. Okay. Another thing, there are hints in the observations that we might be seeing star formation in streams. This is by Ginolfi et al. 2017, who sees star formation along a filament around a massive halo at redshift 3.5. He claims that this is not associated with any galaxies, but is associated with the streams. And my final point, okay, this is the Muse observation of a redshift 6.6 very massive halo with an extended Lyman alpha filament and a Lyman alpha emitter located along the filament falling into the galaxy. Now, is this a merger? They thought so, and you know what? Maybe it is. But you know what? Go back 15 years, and when we started seeing the clump clusters and the chain galaxies, everyone thought they were mergers too. Until the observations got better, the models got better, the theory got better, and Avishai came up with the term violent disk instability, or VDI, which we now all believe is the truth. So just keep an open mind, and maybe when we come back here in 15 years, we'll be calling this violent stream instability in clumpy streams. Okay? That's all I'm going to say. Now, my summary: streams are cool in more ways than one. Kelvin-Helmholtz instability is important for their for the evolution. Streams can disrupt if they're less than 5% of the virial radius. It can drive a lot of turbulence. It can decelerate the streams and fuel Lyman alpha blobs. At high redshift, streams can cool and fragment before they reach the halo center. Implications for globular cluster formation, galaxies without dark matter, reionization. We are currently exploring KHI with cooling, self-gravity. The next talk by my student Han Ong, a great talk, you should stay tuned. And in the halo potential, simulations of stream fragmentation and stream collision with Daisuke Nagai at Yale. Study stream properties and fragmentation in streams together with Nagai, Michael Tremmel in the audience, and another student at Yale. And cosmological simulations with refinement on streams, which we will hear about later today. Thank you very, very much.
Okay. I have a question on what do you predict for cool streams in different cases depending on the environment. So you have studied Borinova, where she finds around radio quiet AGN, she finds these Lyman alpha blobs around the radio quiet AGN. She had also had radio loud, and at Z larger than 1.5, you find galaxy over density around radio loud that are candidates for cluster and protoclusters at zeta larger than 1.5 to 2.8, like the Carla survey. So if I observe at the Carla survey clusters, right, and there is an AGN in the center, I will also see a Lyman alpha blob, and I will say this might be a cold stream accreting. If I have this observation, an observation from Borinova, which difference do you predict I should observe if I am or not in a cluster or protocluster environment with respect to an AGN that isolated and do show also a large Lyman alpha 100 kiloparsec blob?
That's a great question. Just to make sure I understand, you're asking what would the difference in the stream properties be if you're in a protocluster environment or a more isolated environment? Yeah. I would imagine, although this should be studied a bit more, I would imagine in the protocluster environment the streams are going to be denser and are going to be more prominent than in the isolated environment. How that would affect the Kelvin-Helmholtz instability part, I'm not sure that it will, because I imagine the density contrasts and velocities should probably be the same, at least at high redshift. But that's something that our models are just now really beginning to enter the phase where we can answer these questions. Up until now, they were very idealized. So hopefully next year I can give you a better answer.
Okay, so you will put a warm environment around?
Right, so that they already have a warm environment around. Yes.
So what will be the difference? Because if you already have the warm environment around, what would you give as an input to the model to make the difference? Well,
I mean, in the Kelvin-Helmholtz model, the warm environment was what was creating the shear. It was the shear between the cold stream and the warm environment. So that was already accounted for. If you're asking what happens with streams with no warm environment, okay, then the Kelvin-Helmholtz picture should probably not be relevant. Although, wait for Hans' talk with Kelvin-Helmholtz plus self-gravity. The second part about the gravitational fragmentation of streams I think will still be relevant, and that would just affect the range of the parameters. I said there were 3 free parameters there. That would affect the range of the parameters. We can talk more offline.
Okay. Time for one last question while the next speaker set up.
So I really like your enthusiasm, I have to say. You were jumping
I get that
around.
from you, Andy.
Thank you. Is this a compliment?
Yeah.
Okay. So I was wondering, your time scales are given by the fact that you have the fastest growing mode of instability. Now, in real life, you already are highly clumpy, highly irregular, so you don't have to wait till any mode is growing from very small perturbation amplitude. How would that change your time scale arguments?
Right, so when we did the nonlinear analysis, we in some sense implicitly accounted for that, because when I computed the time scales that gave me the maximum width of the stream that could survive, we ignored the linear part. Because we basically assumed that you were already, your like linear modes had already grown, and which is what's the delta t nonlinear. But although we, again, at least in the simulations, we are still starting from linear perturbation, so we have to run simulations that start nonlinear. We haven't done that yet.
Okay, let's thank Neil again.